Okay, pre-calculus honors. This is Mr. Berto doing our first virtual lesson here on YouTube. First and foremost, hope that everybody is home and safe and healthy. Okay, this is going to take probably a little bit of getting used to, all right? But I'm used to just teaching in class and talking and having you guys not understand what the heck I'm talking about anyway, so this really shouldn't be any different. Just kidding, okay? As far as just some housekeeping, I know we had, that last chapter that we went through, you did a review ditto, hopefully, not last week, but the week before, and you did, checked your work with the review ditto solutions. I don't know if we could have a test on that, okay? If I'm going to do like a take-home test or something like that, we're going to have a department meeting on Monday, and we'll discuss what we're going to do with actually grading stuff like this. So try not to freak out about grades right now, and just try to worry about actually learning the material, because we got a lot of stuff to get through. Want to make sure that you're prepared next year for college calculus or advanced placement calculus, okay? So we're just going to jump into the next chapter here. Please, on my webpage, download the dittos, okay, and then print them out so you could use them in concoction with this video. If you don't have a printer, I understand that. You could always look at, a PDF, okay, and then actually write down on a blank sheet of paper. Do the best you can, okay? What we're going to go into is, we've been talking about the derivative. We're actually going to start applying the derivative. Technically, that's chapter 3. If you're in your notes, you want to write that down. We'll be talking about chapter 3, and that's applications of the derivative. We've been talking about a little bit the way the derivative applies, okay? We've talked about how it's the slope of the function, instantaneous rate of change, okay? We'll start to apply that in some abstract settings in this topic, and we'll transition that into some real-world settings in next topic, okay? So this is chapter 3, applications of the derivative, and there's going to be a lot of different iterations of this chapter. There's a lot of different ways you can apply the derivative. Today we're going to be talking about, in this chapter, we're going to be talking about curve sketching, which is really the idea of sketching a function without using a calculator, okay? Remember we had that chapter when we used the graphing calculator, and I told you that eventually we would end up, doing a chapter where we don't have the graphing calculator anymore. Well, here it is right here, okay? So, let's have some fun and see if we can handle this stuff without the graphing calculator. So if you actually jump to your ditto, okay, here we have applications of the first and the second derivative. We'll only talk about applications of the first derivative today. Technically, we're going to do the first derivative test, okay? So back in your notes, you want to put a little star, okay? And right here, we're going to be doing the first derivative test. First derivative test. All right, so if you look at the ditto, okay, we got a wonky looking function here. Okay, we can see it's defined on the closed interval a to g, egg. And here's y equals f of x. And this is Mr. Martina's handwriting. That's my mentor math teacher. I know I've spoken about him before. And you always want to talk about a graph moving from left to right, because we're going to start talking about where a function is increasing, where it's decreasing. You want to talk about that moving from left to right. I know with limits, sometimes we move from right to left when we're examining the behavior of a function, but just be careful. And look, if you're going to talk about graphing a function, well, you could plot an infinite number of points, which obviously will take you forever and you'll never be finished, but you could plot, hundreds of points and connect them, and that'll be a good idea, great way to actually get an approximation of what a function looks like. It'll just end up taking forever. Okay, so what we want to do is we actually want to focus on the key points, the points that are important, and in between those points, then a function is either going to be increasing or decreasing or remaining constant, which we could see doesn't happen with this graph right here. But those important points, we call them critical points, okay? Critical is another way to say important. Situation is critical. That means that it's important, okay? So these are your important points, and the derivative can tell us about important points on f, where f prime, f's derivative, is either equal to 0 or is non-existent. That's where important things are happening, okay? So there's really two different types of critical points. We've discussed both of these, okay, without a shadow of a doubt. And I know my phone casts a little shadow over here. You'll just have to deal with it. That was apt, wasn't it? So without a shadow of a doubt, we know to figure out, where f prime is equal to 0. It's when a function has horizontal tangents, right? When the slope is equal to 0, horizontal tangent line. And look, there are two types that you can ascertain with the naked eye. You could ascertain your rounded local maximums and your rounded local minimums, okay? Those are places where a derivative is equal to 0. There are two other situations, that increasing to increasing situation or decreasing to decreasing situation. Here at x equals e, We got that increasing to increasing situation. You can't ascertain that with the naked eye, okay? Like you can with the horizontal tangent lines here and here. They would have to tell you, okay? You know, either in written text or a teacher that's telling you, and that's what I'm doing right now. Okay, so at x equals B, C, and E, we have the type of critical point where you have a slope equal to 0, a derivative equal to 0. You can also have a derivative non-existent. You know, remember where a derivative is non-existent, okay? Those sharp points, either a cusp or a corner, also vertical tangent line, also points of discontinuity. You could see, you know, with the naked eye right here, that there's a sharp point at x equals f right here. That's definitely a maximum, right? The function changes from increasing to decreasing, but it doesn't attain a slope of 0. It's not a rounded maximum. It's actually a maximum at an x value where the slope of the function does not exist. That'd be x equals f. There's actually one more here at x equals d. That's a vertical tangent line, only because I'm telling you, okay, you can't ascertain something like that with the naked eye. They would let you know. So make sure when you take a test that you actually, you know, read what's going on with the graph. So at x equals d as well, we have a critical point. And we're just labeling the x values here. You know, a point's not just about x values, it's also about y values. But believe it or not, if you just label those x values, we call those critical x values. And that's when your derivative of a function is equal to 0 or it's non-existent, okay? They usually just ask you to find critical x values. If you want the corresponding y values, always plug back into the original function. Remember, the original represents y values. You know, here we have two things that the first derivative function will tell you. It's why we call it the first derivative test. We'll start at the bottom. It tells you where a function f is going to be either increasing or decreasing, okay? Because remember, derivative represents slope. If a slope is positive, you're increasing. If a slope is negative, you're decreasing. Even better than that, you know, a slope's a rate of change, okay? And the rate of change of f represents the rate at which f is changing. F represents y values, okay? A function always represents, I know you're all saying at home, y values, okay? So if you actually talk about the rate of change of f being positive, when something's rate of change is positive, it's getting bigger. And if y values are getting bigger, that means that a function is going to be increasing, okay? And if the rate of change of f is negative, that means that f is getting smaller, which means the y values of f are getting smaller, which means that f is actually decreasing, okay? So you could see here that where f is increasing when f prime is positive, when his derivative is positive, and f is decreasing when f's derivative is negative. You know, they want to know further down on the paper, where is f increasing, where is f decreasing? Should be pretty easy, okay? I'll put f increasing here, or f incorporated. And you could see on your graph, that's occurring from x values of a to b. And then we could say from c all the way up to f, okay? It is true that the derivative is not positive at d and e. You know, the derivative is non-existent and equal to 0, respectively. But you can still increase if your derivative is non-existent, and you could still increase if your derivative is equal to 0. So you could split it up and say you're increasing from c to d, d to e, e to f, but you could also say you're increasing all the way from c to f, and don't forget about a to b, okay? So from a to b, and then from c to f. And I never include the endpoints when you're increasing or decreasing. Like I said, some teachers do, okay? On the AP exam, they'll never have one answer being inclusive and one answer being non-inclusive, so you don't have to worry about that. Whereas f decreasing, you can see up here on the graph, it's definitely decreasing from b to c and from f to g, okay? So f decreasing, we know from b up to c, and also from, I might have said e to g, I meant f to g. Oh, right. You know, and you can see, even if you go from f to g, if you draw a tangent line there in the graph, pick any point that you want, draw the line tangent, you could see the slope is negative, okay? If a function has a negative slope, that means the function is decreasing. And if you know about increasing or decreasing, then you know about your extrema, your max-min points. We talked about this, okay, back in that calculator chapter. Extrema, which is extremely important. I thought that was funny. There's really three types, okay? Mr. Martina has your local extrema, which you also call relative extrema. Remember, that means you can look a little bit to the left, a little bit to the right, either see points below you or points above you. But then there's also endpoint extrema, so make sure you add endpoint extrema. Some people consider local or relative extrema, endpoint extrema. I like to split them up a little bit. I think it makes answering questions a little bit easier. And then you get to compare the y values of your local extrema and your endpoint extrema and get your absolute extrema, which is your global extrema. We'll do that with calculus in a couple minutes. Right now, they just want to know what are the max-min points on f, okay? So we'll actually break it down this way, and I'll be like, okay, let's do our local maxes first. We'll just talk about the x values. You can see we got a local max here at x equals b. You look a little bit to the left, there's points below you. A little bit to the right, there's points below you. OMG, I'm a max. And that also happens at f right here. Two different types of maxes, okay? One where the slope is equal to 0, one where the slope is non-existent, okay? So that's going to be x equals b and x equals f. And then we want to check for endpoint maxes, of which you can see here, both the endpoints, they represent a min, okay? This is the lowest point in his little area right here. There's only points above him. Just like over here, there's only points above him. So as far as endpoint maxes, none. And that means if you want to talk about absolute maxes, well, you want to compare, okay? Your local maxes and your endpoint maxes, compare the y values. Here we only have the local max at x equals b and x equals f. You can see that at f, it has a higher y value, hence it's the absolute max. Okay, remember, he's also a local max. This is just an additional title that he takes on. You want to talk about mins, we got to talk about local mins first. Local min. All right, we can see that occurs at x equals c on the graph right here, a little local minimum. And we know that there are endpoint mins at both endpoints, okay? So x equals a and g. And then if you want to know where your absolute mins are, your absolute min, there could be more than one, remember, if they're tied for y values. But you can see here by the graph, it's obvious that the lowest y value occurs at x equals c. All right, so that's supposed to be quick review. Hopefully it's not too terrible. Is f continuous everywhere? Obviously, you can see it is continuous. No points of discontinuity here. Remember, a function being continuous doesn't imply it's differentiable. You can see at x equals f, it is not differentiable, okay? But remember, if they do tell you a function is differentiable, that does imply that it's continuous, okay? Let's actually do a couple sample problems here, okay? So what I want you to do is pause the video, copy these two problems down right here, okay? And then pause the video and copy this problem down here, okay? So make sure that you're able to do that, and then we go rock and roll. All right, so if you actually want to talk about in the first example over here, they want you to find the critical x values of f. And remember, the critical x values of a function are going to be where that function's derivative is either equal to 0 or that function's derivative does not exist. All right, so sometimes they just actually want you to find those critical x values. We'll do that in A and B. And then in the other example right there, we'll actually talk about how this is going to help us sketch the function and know about what's going on graphically. Here we have f of x equals nice little polynomial function right here. And if you want to find critical x values of f, and you want to find where f prime is equal to 0 or f prime is non-existent, you'll need f prime, right? So let's derive. I will derive. We get f prime of x equals what? 3x squared plus 12x plus 9. Okay, and this right here, you want to check to see where it's non-existent, but it's a polynomial function, okay? A polynomial function exists everywhere. So this thing exists everywhere. You don't technically need to write that down, but you got to remember that, you want to check to see where derivative is non-existent, but there's no x value I can plug in here that yields a non-existent result. You could have looked at the original function and said, hey, that's polynomial as well. Polynomial functions, besides being continuous everywhere, differentiable everywhere. So obviously their derivative is going to exist everywhere. Here it's really about setting the derivative equal to 0. Little factor action, right? I'd factor out a 3 right here. So what, x squared plus 4x plus 3. And you can even cancel that 3 out right there, right? Divide by 3 on both sides. Got some ghosting here with this ditto on the bottom. I don't like the way that looks. Take care of that. I ain't afraid of no ghost. Your parents will probably get that reference. Anyway, or Peter Stavros, he got that reference. So let's put x and x right here. Little factor action. Last sign is positive. Both signs can be the same as the middle sign. We know it's 3 and 1. Pretty easy factoring right here. Even Connor Crowley couldn't complain about that, even though he's probably complaining right now. Actually, more likely he's calling me a nerd. All right, so here we have x equals -3 and x equals -1. Those are your critical x values. If you actually wanted the critical points, you want to take those right there, plug them back into the original, which could be infinitely annoying without a calculator, but something you have to be able to handle. Part B, different function, right? Radical function, well, f of x equals radical x. We want to find those critical x values. Well, that's where the derivative of the function is equal to 0 or non-existent. Here, I wonder if you actually memorize the derivative of radical x is 1 over 2 rad x, okay? It's a great way to do the problem. You could say radical x is x to the 1/2. take the derivative 1/2 times x to the negative 1/2, but we're going to have to play around with this, okay? Find out when it's equal to 0, find out when it's non-existent. Easier to do it this way. And this is a fractional derivative. And a fraction, if you actually want to find out when a fraction is equal to 0, believe it or not, you just set the numerator equal to 0. Fraction is equal to 0 when its numerator is equal to 0. If you don't believe me, take the entire fraction, set it equal to 0. You know, what are we going to do here? You could multiply by 2 radical x on both sides. That's what Mr. Harrington would like you to do. If you want to actually draw the ire of Mr. Harrington, quite literally, I'm going to draw the ire of Mr. Harrington by turning this into a proportion, cross-multiplying. 2 radical x times 0 is equal to 0. 1 times 1 is equal to 1. And there's no x value that will make 0 equal to 1. If 0 is equal to 1, like I've said many times before, I could eat 1 cheeseburger every day, 1 double cheeseburger, and it'll be like I ate 0 double cheeseburgers. Not showing myself in these videos, just by hand, but, you know, you all know what my stomach looks like, and there's no way that, you know, I could eat 1 double cheeseburger a day and have it be 0 double cheeseburgers. Anyway, I went off on a tangent there, but really totally apt in a calculus class. If you want to find out where a fraction is equal to 0, set the numerator equal to 0. Set 1 equal to 0, you'll see that there's no solution right there, but a fraction being non-existent, that's not when the numerator is equal to 0. That's when the denominator is equal to 0. It should be something you guys could all handle. Divide by 2 on both sides here. Okay, and we'll get that radical x is equal to 0. Square both sides, and I get x is equal to 0 squared. Now, if you want to see what's going on, we'll just square both sides. And we know 0 squared is just 0. So x equals 0 is actually a critical x value here. It's you know, a place where the function's derivative is non-existent. Okay, so that's what's going to happen with a non-existent derivative algebraically. It's probably going to be some kind of x value that makes a denominator equal to 0, or perhaps makes, you know, a negative under a radical, something like that. You know, moving on to this problem right here, let's do the fun stuff, okay? Here they give us a polynomial function f. They want us to find critical points of f. We know how to do that. We just did it. Then they want you to find where f is increasing or decreasing, and also the extrema. And then we'll even make a quick little sketch of the function here, okay? So look, you know, take it step by step. These are very long, drawn-out problems. Here, critical points. We know we want to take the derivative, which we know is equal to 3x squared minus 12. It exists everywhere, okay? It's never non-existent right here. Sometimes I write never DNE, which really is kind of silly because you're saying never does not exist, but I guess technically that's correct, even though it's kind of weird English there. But set it equal to 0, which we also know is Mr. Pushy's IQ. Factor out this 3. You could even cancel out that 3, right? Divide by 3 on both sides. And then a little factor action. Okay, and we get that we actually have critical x values at x equals -2 and x equals +2, okay? But those are just the critical x values. We want the critical points. So if you want crit points, remember, if you want a y value, you always plug back into the original, very good, the OG function. You always plug in there for position. So 2 comma f of 2 would be crit point, and also -2 comma f of -2. You know, to plug a 2 into f, okay, you know, 2 cubed is going to be 8 right there, minus 12 times 2, which is going to be 24. Okay, so 8 minus 24 is going to give us our answer of 16. Oop, -16, pardon me. You know, and now, if you actually draw on your knowledge of even and odd functions, this is an odd function, hence f of -x is going to be equal to -f of x. So that's a way to know that you're going to get a positive 16 when you plug in here. Try not to go too crazy with that. They don't really focus on that on the AP exam all that much these days anymore. But knowledge of even and odd functions can reduce the amount of mental math that you'll actually have to do. So something to think about. So those are critical points right there. And now people are like, okay, well, how are we going to find where f is increasing or decreasing? Well, we talked about that. All right, a function is going to be increasing when its derivative is positive, and a function is going to be decreasing when its derivative is negative. And we have some information about the derivative here. Remember, if the derivative is neither positive nor negative, that means it must equal 0 or be non-existent, okay? And we know it's never non-existent, but we figured out places, x values, where the derivative is equal to 0. Now we got to figure out where the derivative is positive and where the derivative is negative. If only there were some way to have some kind of graphic organizer that you could draw out that'll tell you information about a function when it's positive, when it's negative, when it's equal to 0. Sound familiar? We did that with the velocity function, okay? Remember? This is where I draw the line. You know, I'm on a carpet here, so I can't really make the same kind of noise that I like to make in class by stomping my foot. And if I smash this table, my phone's going to end up falling down. But this is where we draw the line, not the V line, because I don't want information about velocity. Who talked about velocity here? Even though this is an abstract form of velocity, right? Because it's the first derivative. But I want to draw the F prime line. You want to think to yourself, "'Tis it bounded?" And you can see that's not, okay? F's domain right here is all real numbers. You know, we drew that velocity line. It would be bounded on the left-hand side by 0 because time can't be negative. Sometimes bounded on the right-hand side, okay? But, you know, sometimes not. But here, this is abstract. And on the F prime line, you want to put all the places where F prime is either equal to 0 or F prime, pardon me, does not exist, okay? And you can see that this is a place where F prime equal to 0. Sorry, breakfast coming back there. That's disgusting. Okay, and, you know, at -2 and at +2. And remember, if you want to find out where F prime is positive or negative, just plug into F prime. I'd plug into the factored version over here, maybe plug in like a -3. -3 plus 2 is going to be negative. -3 minus 2 is negative, but a negative times a negative is a positive. So doing this just like we did with the V line, if you plug in 0, okay, 0 plus 2 is positive, 0 minus 2 is negative, positive times a negative is a negative. And if you plug in a 3, 3 plus 2 is positive, 3 minus 2 is also positive. Positive times a positive gives us a positive. So that's where F is increasing or F is decreasing. F is increasing where F prime is positive, okay? So F increasing, and that's going to be from -infinity up to -2. And also on the Buzz Lightyear interval, to infinity and beyond, which is impossible. And then, you know, F is decreasing because it has a negative slope, and that's going to occur between -2 and 2. So we don't need no stinking calculator. We just need the F prime line. Make sure you label it the F prime line, okay? Because in a couple days, we're going to have the F double prime line. It can be very confusing. People are like, well, what do I plug back into? It's simple. If it's the F prime line, you plug back into F prime. If it's the F double prime line, you plug back into F double prime. The only time you ever plug back into F, the original, is to get Y values, okay? So if you practice, you'll be all right here. And then they want to know, you know, there's increasing or decreasing. Now they want to know about extrema. We got to think about it a little bit here. You might notice at -2, F prime is equal to 0. That means if you were drawing the graph of F, this fictional graph of F, we don't know what it looks like, but we know it has a slope of 0 at -2. We also know the slope changes from positive to negative at -2. And if your slope changes from positive to negative, that means you change from increasing to decreasing. So if F prime changes from positive to negative, that means F, this function right here, changes from increasing to decreasing. So that's actually a local max. And here at x equals 2, F prime changes from negative to positive. That means that the slope of F changes from negative to positive. That means F changes from decreasing to increasing. And that's a local min right there. There are no endpoints. This graph starts its life by having a positive slope. So it starts its life by increasing. So there's going to be some arrow here that starts, you know, somewhere down at -infinity. And this thing is just going to be increasing. Then it's going to change to decreasing. It's going to top out. Then it's going to change to increasing again. And then it's going to increase from the rest of its life. Not so easy to do. The sketch is always the hardest part, but identifying extrema is important. And it's going to take a little bit of time for you to get used to. But now I know that we have no absolute extrema, right? Because this thing comes from -infinity, shoots up to +infinity. But I know I got a local max. Some dude named Max lives next door. We know that occurs at x equals -2. And if you want the point, we know that's the point -2 comma 16 because we did that before. And if you want to talk about a local min, we know that's going to occur at x equals +2. And we actually know the point. We know it's 2 comma -16. Sometimes they just want the x value. Sometimes they want the coordinates of the point. And look, that's all you have to do for this problem right here. So believe it or not, it's really not too terrible. You know, to tie it up right here to just end the lesson. You can have another one like this for homework. We'll do the sketch. Sketch! You know, you're not supposed to do the sketch right now. This is highly dangerous because we don't know information about how the function increases or decreases. Does it increase looking like an N? Does it increase looking like a U? That's concavity, okay? That's something we'll talk about on Wednesday in that video. But we can kind of cheat here a little bit because it's a polynomial function. You know, draw that X and Y axis. Okay, and we'll just plot our points here. Always start by plotting points. What kind of points do we have? Critical points, okay? You know, we know that 2, negative 16. You could have a point over here. And then we know at negative 2, positive 16, you could have a point, so maybe like somewhere up there. You know, we also know that at x equals negative 2, we know that there's going to be this little local max right there. Looking a little something like that. Wow, that's drawn terribly. Okay, but don't worry, we got white out here. We got an eraser on the whiteboard. I got white out right here. And then also at 2, negative 16, we know this thing's going to bottom out. There's going to be a local min. We also might want to get a y-intercept just for kicks and giggles, right? You know, let's do f of 0, which is going to give us 0. If you plug 0 back into the original function, means that 0, 0 at 0 is going to be a point. That's an easy point to plot. And look what happens here. We know that f, because f prime is positive, f is going to be increasing from negative infinity to negative 2. So the graph right here is going to increase from negative infinity up to negative 2. It actually increases looking like an N because I know it's going to meet up with this local max right here. We'll find out more about that, like I said, on Wednesday. But now we know the graph is decreasing from negative 2 all the way to 2. It's going to decrease the whole way. Believe it or not, it's going to decrease at first looking like an N. Okay, so forget about this little piece right here. Sometimes I like to draw those little wings on the graph, but they rarely match up perfectly. So that's good enough right there. It actually decreases looking like an N, then it hits something known as an inflection point, okay? And now it decreases looking like a U. You're not supposed to know about that, okay? We'll find out about that on Wednesday. But then we know it increases. Remember the Buzz Lightyear interval? To infinity, okay? So from 2 to infinity, this thing's going to be increasing for the rest of its life. And you can see it looks like that sideways S, which is what cubics technically look like. So with polynomial functions, you can cheat a little bit, but really you need more information than the first derivative test. You need the second derivative test as well to actually be able to know what's going on with concavity. But close enough for government work, okay? You don't need to do the sketch here. Sketch is always the most difficult part. Remember, critical x values of a function f is where f prime is equal to 0 or f prime is non-existent. If you want to know where a function f is increasing or decreasing, and the extrema is where I draw the line. The f prime line, okay? Just like the v line, and just be careful identifying extrema. Not the easiest thing to do, okay? But something that we'll speak about more and more as we go through this topic. So look, you know, do me a favor, okay? You know, get onto my website, join my Remind, okay? I have that set up. I think that's a way we're going to be able to grade you in the future because you can submit assignments through Remind. This is all new. Try not to have any anxiety. The important thing is to make sure you're safe and you're healthy and you're at home. You know, email me if you have any types of questions. If you think these videos don't make any sense whatsoever, okay? Remember, if you think I'm moving too fast, you could always pause. Okay, and then, you know, when you hit play, we'll be right back here, okay? So this is the first video. Sorry it went a little bit longer. They'll be, you know, anywhere from 20 to 25 minutes. But like I said, you know, get in touch with me and try not to have any type of anxiety. And just think about learning, okay? You know, you need this curriculum. Eventually, this is all going to be over with, this virus scare, okay? And you guys are going to be in college or in AP Calculus. You need to be prepared and ready to go, okay? So this is Berto in his first video signing out. Hope everybody has a safe and healthy day. Adios.